Xilinx FPGAs are SRAM-based, using a 65 nanometer copper CMOS process. Generally, the largest FPGA today can accommodate approximately 25 million system gates, including the RAM, logic gates, and I/O resources. Vertex 5 devices can run at up to 550 MHz. The ASIC design suite with integrated synthesis and place and route tools can be purchased for approximately $2,500. That does not include the optional hardware simulator, I might add. The ASIC design suite can be used on both PC and Unix machines. FPGA tools are very inexpensive when compared to ASIC tool sets, which would probably cost a lot more. Note that most experienced customers use a third-party hardware simulation tool to test their FPGA design. This is strongly recommended and is not included. Likewise, many Xilinx customers use our integrated logic analyzer, ChipScope. This is also an additional software suite. Each of Xilinx's tool sets is available on a trial basis. This includes the ASIC Webpack, which supports most of Xilinx's devices and is entirely free for life. While the Webpack does not include all of Xilinx's tools, it is very suitable for many customers. Configuration must occur on power-up, but can also occur on demand. This is done by toggling the FPGA's programming pin. FPGAs must be configured because their SRAM cells are volatile. The user will have to plan on storing their configuration data, commonly called a bit stream, in a PROM, an SDRAM, or some other external data source. This, of course, will cause some additional cost to your final system. To build your system, you'll have to understand the basic configuration process and how to set up various configuration modes and daisy chains. But before you can get to that point, you will need to understand the advantages and disadvantages of each configuration mode so you can choose the appropriate one for your system. You may also need to gain some knowledge of how a series of FPGAs can be daisy chained to use a single memory source, just in case your system requires multiple FPGAs. As was mentioned earlier, reconfiguration of the FPGA allows the device to be modified, fixed, or the design upgraded without wasting the device. This extends the life of the product a great deal. But most importantly, it enables a faster development time to our customers. Instead of lengthy development times, they can simply make the design change and program the same device. There have also been plenty of applications where a single FPGA was reprogrammed in system with a different bit stream to enable the FPGA to serve multiple purposes at different times. This has given way to the concept of partial reconfiguration. Partial reconfiguration allows part of an FPGA to be reprogrammed actively while the device is operating. To illustrate, take a laser printer. You could build a controller as part of the FPGA design and have a series of buffers that are reprogrammed actively, based on the font or paper size the user selected. Now this might allow a smaller FPGA to be used since the buffer could be reprogrammed quickly from an external memory source, and only the buffer that was needed at the time would have to be programmed into the FPGA. While partial reconfiguration is a very cutting-edge technology, it is not necessarily suitable for many customers. It is fascinating, and hopefully this example gives you an idea of what partial reconfiguration means. There are lots of configuration modes you can choose from. They are all equally valuable and allow our customers to choose a configuration scheme that is right for their application. First, users should always consider configuring their device via a Xilinx download cable. These cables allow the user to reconfigure their FPGA with only a download cable on their computer. The configuration modes that use these cables are used primarily for prototyping and debugging. These cables are low cost and are typically used to configure the FPGA in a JTAG configuration mode. Configuration can also occur with the use of a microprocessor or microcontroller. These configuration schemes involve some other external control logic being used to control the configuration process. In these configuration modes, the FPGA is a slave to whatever control logic is managing the configuration. These configuration schemes require extra components and thus have added cost associated with them. Most users consider this configuration scheme if they already have the external control logic available as part of their system. Configuration can also be completed using the Xilinx Platform Flash PROM. These configuration schemes usually use the FPGA's built-in configuration logic to control the FPGA's configuration. With these components, the FPGA usually configures itself. These configuration schemes require the user to buy a PROM, which has some additional cost, but these configuration schemes are usually the easiest to debug since the control logic is already fixed as part of the FPGA. We will talk about the Xilinx Platform Flash product in the Basic FPGA Configuration 2 module. Some new configuration options have just become available to Xilinx users. The Serial Peripheral Interface, SPI, and the Byte-Wide Peripheral Interface, BPI configuration schemes allow users to purchase off-the-shelf commodity flash components. The flash memory can then be used to store the configuration bit stream and for the user's application memory, if the user is building an embedded system. Note that to this point we have discussed having only one configuration mode. In reality, most customers want to debug their prototype and then later program the FPGA with a different configuration scheme. To do this, most designers build some simple control logic which will allow the system to switch between the 2 or 3 configuration schemes of choice. Alright, so let's take a look at the basic architecture of Xilinx FPGAs. The first and most significant resource is the CLB, or Configurable Logic Block. The CLB contains registers and LUTs, commonly called lookup tables. The LUT is your primary combinatorial logic resource. We'll discuss the LUT and the contents of the CLB further in the next couple of slides. Throughout the FPGA are columns of block RAM, DSP slices, and other dedicated hardware. This includes PCI cores, eMAC blocks, perhaps a PowerPC processor, and other dedicated resources. Since the type and quantity of dedicated hardware will vary by product family and density, it is a good idea for you to flip through the datasheet to help you decide which device family is right for your application. IOBs, or input and output blocks, contain registers and other specialized resources that are designed to help interface signals to the outside world. Every input and output signal in the design must go through an IOB. The IOBs also have a programmable I/O standard functionality that supports up to 40 different I/O standards. So each pin has a programmable interface that is programmable on a pin-by-pin basis. Outside of the CLBs are large arrays of routing resources. The routing is connected together with switch matrices. The switch matrix allows many different lengths of interconnect to connect a signal from any source in the FPGA to any destination. This structure is designed to assure routing flexibility so that all designs can route to completion. It is also designed to assure short routing delays so that system performance objectives can be obtained. To aid the software in the effort of obtaining desired performance, Xilinx supports the use of timing constraints through its ISE design suite. Timing constraints allow designers to specify their desired timing objectives, which the tools will then use to guide the placement of logic and the assignment of routing. Another significant resource is the clocking resources. Vertex 5 includes DCM, or digital clock managers, and PLLs, or phase lock loops. They also have dedicated routing resources that are used for the distribution of clock signals with minimal skew. DCMs are used for clock signal generation, while PLLs are primarily used for the removal of clock jitter.